And now a property among the properties of logarithm says the following. If we take log base a of a quotient x over y, this logarithm of the quotient here can be equal to log base a, notice the same base again, log base a of x, the number in the numerator, minus log base a. So here, instead of taking log base a directly of a quotient, we're taking the difference of two logarithms, same base, log base a of y. So log base a of x minus log base a of y here. This property is known as the quotient to, so quotient, because we started out with a problem taking logarithm of a quotient, but we turn that into a problem where we take the difference of two logarithms, same base. And so that's why it's called log quotient to difference. Quotient to difference rule. And now on the same property, we can also think of going from a difference of two logarithm terms, same base. So log base a of x minus log base a, same base, of y. But it's a difference of two logarithm terms. We can go from a difference and turn that into one logarithm, but of a quotient. The two evaluation works will come out exactly equal value. And so this other rule I just now introduced is also referred to as the difference to quotient rule. It's just the opposite way of thinking about this same property versus the earlier form that was introduced. There is a formal proof to explain why this property is true. However, for the practical usefulness of this short lesson right here, then we don't need to see that the formal explanation here. So anyone learning from this lesson will get a chance to understand clearly how to use this and how useful this property is in some of the direct examples as following. So now let's look at one example where we want to do a basic computation problem. So let's evaluate. So in part A of the example, let's evaluate log base 10 of 50 minus log base 10 of 5. And so simply looking at this evaluation problem, then anyone will naturally think about we must obtain the logarithm values for 50 and the logarithm value for 5 before we do the subtraction. And that is totally agree. And so with that thought right there, for anyone who has a calculator that is strong enough or advanced enough, then you can do the following. As far as those calculators that can do the exact same problem in one command, then we do log base 10 of 50 minus log base 10 of 5 and hit enter. The answer comes out 1. But this solution using the calculator is only for those people who are, or is only for anyone who is having a calculator that is quite advanced. And so in case your calculator is not as advanced as the one I've shown earlier, we can do two separate steps. One step is for log base 10 of 50 and get an answer for that, which is expectedly a very ugly looking decimal expression right here. And then that answer previously we will subtract with the answer that comes out from log base 10 of 5. And we will get to this answer 1. So expectedly log base 10 of 5 will also be another ugly looking decimal value, but somehow subtracting the two answers will come out a very nice value here. And then for anyone who doesn't have a calculator that is as advanced as the one I've shown on the computer screen, then we have to think about getting our work done effectively, because calculating the two logarithms here is in no way easy at all, and then make a subtraction afterwards is going to be a lot of steps for you. So in that case, knowing the property here will be extremely useful. And so now I'm talking about without an advanced calculator, we can do the following. Manipulating this property, so here I'm starting out with log base 10, but it's a difference of two log base 10 problems. And so I can use this property in a way that I go from a difference to a quotient. And so now that means I can create the following problem. Evaluating this is the same or equal to evaluating log base 10 of the quotient 50 over 5. So be careful with the order of with the order in this difference right here. So when it's log base a of x minus log base a of y, then in the quotient we need to put the x in the numerator and the y in the denominator of the quotient, just like how I did that here. And so now this is a little further from the inside out. 50 over 5 is a 10, so it's the same as log base 10 of 10. The answer now comes out without any assistance from a calculator. Log base 10 of 10 equals 1. And now I moved on in this problem here completely without the need of using a calculator. And now in the next problem of the same example here, let's look at log base 3 of 72 minus log base 3 of 8. All right, and so now for a problem like this, doesn't matter if anyone is having an advanced calculator or a very basic calculator. Generally, we just don't have a key available for log base other than e or 10. And here in this problem, we're asked to evaluate log base 3 and log base 3. And so definitely if we go with that route where we punch in log base 3 of 72 and then with whichever answer that comes out from here, subtract log base 3 of 8. That is not of a choice for us any longer in a problem like this. But then thankfully we have this property that we can use similar to how I used that in part A right there. So now we can go from a difference of two logarithms, same base. I can rewrite that as one logarithm, log base 3. And now inside of this log, I'm going to create a quotient, 72 over 8. So once again, the order of the two logs term here implies the order in the quotient here. So 72 comes, 72 was part of the logarithm term before the subtraction. So now in the quotient here, 72 stays in the numerator, whereas 8 is in the denominator. So 72 divided by 8 is a 9, so we're looking at log base 3 of 9. The answer now comes out equals 2. And so now we can do this problem a lot faster and a lot more conveniently using our understanding of the difference to quotient rule, or sometimes we may use the quotient to difference rule instead of using a calculator. Let's now look at another example where we're asked to evaluate. So this is another example where we're just doing further computation problems. So there will be times we're asked to find natural log of a quotient. So how about 1 over 25? Allow me to share my experience, but a problem like this will admittedly come out in no matter in which way you're trying. A problem like this will come out in a very ugly looking decimal value. But at least if we're typing an expression like this directly into the calculator, we will run into the following command, regardless of whether you're having an advanced calculator or a more basic kind. Natural log. So that takes one operation, and then inside of the logarithm, 1 divided by 25. So it takes one operation and two operations, and we divide, and we end up with a value negative 3.218875 and a lot longer. So I'm talking about we already had an answer, but now we think about as an effectiveness of how we use the calculator on top of what we have already learned about the rule here. We can, before we use a calculator, we can effectively rewrite this as, notice how that is a quotient. So we can rewrite this as a natural log of 1 minus natural log of 25. Now currently I'm explaining a lot of thought process here, so it seems to slow down a little bit of the process. But once you get fluent with this, it will be a lot faster. But now natural log of 1, according to the earlier property that we have learned, then this is going to be simply a 0. So our problem turns out to be simply just a negative of natural log of 25. So now if we are entering this into a calculator to obtain the final decimal value, then it's going to be a lot faster to type this in. So on the calculator, we can just simply go natural log of 25. And then think of that answer here as a negative answer, because we already knew that the answer must be negative, or the opposite of natural log of 25. So now the answer will come out negative 3.218876. Allow me to stop at 6 decimal places here, but it will be a lot longer. And that's how we can calculate. But so admittedly we had to use the calculator to come up with this value, but we can use the calculator with a lot less typing, with a lot less operations involved. And so now, even though being part B of the same example, it's just another repeated try for any one of us here. So let's now look at log base 10 of 1 over 3. And so before we think about using a calculator, we definitely don't want to type log of 1/3 in the calculator. We don't want to go that route. It's going to be a lot longer. Log base 10, which is available with any calculator, inside the parentheses is 1 divided by 3. We don't want to do this because it will take a lot of time. So with this rule over here, going from a quotient to a difference, I can rewrite this as a log base 10 of 1 minus a log base 10 of 3. Just very similar to how I did this in part A. And so now with this difference right here, the first term is simply 0. And so that leaves me negative log base 10 of 3. And so now typing this log base 10 of 3 in any calculator will be a lot faster than log base 10 of 1 divided by 3. So log base 10 of 3 here, and write your answer as a negative. So now I'm ready for that calculation. Log base 10 of 3. And this comes out 0.477 12. So the answer is indeed negative 0.47712, and a lot longer, but allow me to stop at 5 decimal places. And as another problem in the same example to add into your own experience working with logarithms, then now when it's log base 5 of a 1 over 12, for example, okay, we definitely don't want to use a calculator, or if we have to, we definitely want to make it more convenient for us before we type it in the calculator directly from here. So back to what I was in the middle of saying earlier, we definitely want to avoid typing directly this command into a calculator as log base 5 of 1 divided by 12, because first of all, there is no immediate key available for log base 5. So we are going to stay away from that route. Now, before we use the calculator for a problem like this, think about, we can rewrite using the quotient to difference rule over here. I can rewrite this logarithm as log base 5 of 1 minus log base 5 of 12. And that means the answer now will be just simply negative log base 5 of 12, because this will be surely 0. And with this final expression here, I can now use a calculator easily. At least if the calculator is not offering a direct key for log base 5, we can still have some work. We can still have some work around that can handle log base 5 of 12, and then the answer will come out as a negative answer. So on the calculator here, log base 5 is not immediately available, so I will go with a choice of log between natural log and log base 10 here. So I'll go with natural log. So log base 5 of 12 equals to natural log of 12 divided by natural log of 5. Okay, and then once we've had an answer for this, the final answer will be negative on my writing board. So this is the answer for log base 5, positive log base 5 of 12. So now back on my board, just make sure to indicate the answer as negative. So negative 1.54396, and allow me to stop at 5 decimal places. So in this current example right here, we are using the calculator throughout all problems, but what matters now is that knowing some log rules can speed up the work process here and save us some efforts typing in a lengthy log command. And now we can look into a different example where we want to expand a given logarithm expression. So let's look at a problem in part A right here. So how about a log base 10 of 3 over x. And so what I have now is a logarithm of an expression. The expression inside the log here is reading 3 over x. But now what we notice here, it's a quotient. So immediately I can use the property that goes from that rewrites a logarithm from a quotient logarithm of a quotient to the difference of two logarithms. So here I can expand this into log base 10 of 3 minus log base 10 of x. And as far as the work to expand the expression, we are done right here. And let's look at another repeated problem here when we're expanding a logarithm expression. So how about log base 2 of a over 8. So what I have here is a logarithm expression, And specifically inside my log base 2, there's an expression being a quotient, which appears to be a quotient, a over 8. So now with our understanding of this property, where we can go from logarithm of a quotient to the difference of two logarithms, I can rewrite, or I can expand this as log base 2 of a minus log base 2 of 8. So as far as expanding the expression, we've had it done right here up to that point. But then anywhere we can, let's go ahead and evaluate into a final value. So log base 2 of 8 can be evaluated into a final value, whereas log base 2 of a is at the end right here of itself. So here I'm looking at log base 2 of a remains the same, but log base 2 of 8 will equal 3, because 8 equal 2 to the third power. So log base 2 of 2 to the third equals 3. And this is now our final answer. But this is in the expanded form compared to the beginning version right here.